Morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, we are going to discuss about the same topic, the electrostatics. In the previous class, that is in yesterday's class, we discussed about the electric field intensity due to the infinite line charge and electric field intensity due to the charged circular ring. And also, by using the Gauss law, we derive the expression for the point charge of electric field intensity and electric flux density d bar. Now we go for the by using the Gauss law, I have to find the infinite line charge, the electric field intensity and electric flux density. So we know the formula for electric field intensity due to the infinite line charge. E bar is equal to so according to the point charge is a q by 4 pi epsilon naught r square into AR bar is a point charge formula for the electric field intensity. By substituting that q is equal to, or the dq is equal, dE bar is equal to dq, that is a rho L into dl by 4 pi epsilon naught r square into AR bar. This electric field intensity due to the infinite line charge we derived directly. That is E bar is equal to rho L by 2 pi epsilon naught R into AR bar. Okay, this is a formula we have to derive the electric field intensity due to the infinite line charge. But the same equation you have to derive by using the Gauss law. My dear students. Okay, for that, consider a infinite line charge density rho L. This is a rho L, my dear students. Here, you see this arrow mark, this dark line showing that there is a charge is uniformly distributed on the z-axis, lying on along the z-axis from minus infinite to infinite. Consider a Gaussian surface as a right circular cylinder with z-axis as its axis and the radius r. See, there is a right circular cylinder is there with a radius of r, and z is an axis of that cylinder. Okay, the length of the cylinder is totally the length of the cylinder is showing that L is the length of the cylinder and radius of the circle, and is a rho L of the charge density on the z-axis. Okay. The flux density at any point on the surface is directed radially outwards. See, the charge is distributed uniformly on the z-axis, means there is a positive charges. From that positive charge, it is enclosed with the cylinder. From the charges, there is a magnetic lines of forces is terminated radially outside in AR bar direction according to the cylindrical coordinate system. So consider the differential surface area ds as shown in the figure. You see here ds, I am assuming a surface here. The positive, from the positive charge, there is a magnetic lines of force is passes through this unit surface area ds in the AR bar direction. Consider a differential surface area ds as shown, which is at a radial distance r from the line charge. The direction normal to the ds is AR bar. So we know the equation in the cylindrical coordinate system, the r phi and the z is a differential surface area normal to the r direction. ds r bar is equal to, means r bar is a direction, ar bar, and differential elements are dr is one differential element, r into d phi is another differential element, and dz is another differential. So the differential surface area normal to the direction of r bar means there is no any differential element of dr, and we have the remaining term sigma product r into d phi dz. Okay, is a ds r bar. Now the infinite line charge we derived by using the Gauss law. What is the Gauss law saying? That the q is equal to integral d bar dot ds bar. Integral d bar dot ds bar. Following my students. So when this cylinder showing that there is a top, side, and the bottom. Okay, the integration is to be evaluated for side surface, top surface, and the bottom surface also. What do you mean? Q is equal to divide this Gauss law in the three parts. One is the side, top, and the bottom. Assuming the d bar is equal to, because it is in the r direction, the unit surface area. Here there is a unit surface area. We are assuming a small unit surface area. The z-axis, the magnetic lines are radially outside through this surface area along the AR bar direction. So I assume the d bar is equal to dr into AR bar as only radial component. ds, what is the ds? That is in the AR bar direction, differential surface area normal to the r direction, r into d phi and dz into AR bar. So using the dot product for here, using the dot product, d bar dot ds bar is equal to, so dr, r, d phi, and dz, ar bar dot ar bar, ar bar dot ar bar is equal to 1. So dot product itself is always a 1. So d bar dot ds bar is equal to dr into r, d phi, and dz. dr is a constant over the side surface, as a d bar has only radial component and no component along az and minus az. Hence, the integrations over the top and the bottom surfaces is a 0. Why it is a 0, my dear students? Top and the bottom means, see, previously I told that there is an equilibrium is there whenever that is a charge is distributed, uniformly distributed on the z-axis means z-axis the topmost and the bottommost, both are, it is a 0 zone. So according to the q is equal to d bar dot ds bar, the integrations, the top integration and the bottom integration, both are the zeros. Okay, consider this is a positive axis and this is a negative axis bottom. So both are is a 0 one. Both are get cancelled, simply saying that. Okay, and remaining only the side, q is equal to integral side d bar dot ds bar and integral of that d bar dot ds bar we got after substituting the d bar as a radial component in the ar bar direction and the ds bar along the r direction, dr, r, d phi, dz. So substitute here the dr, r, d phi, and the dz. Okay. And see, here the phi and the dz only we have. So phi and the dz. So with respect to the phi, the limitations are 0 to 2 pi. And that z we can see the limitations is for the minus infinite to infinite, we know. Actually, the phi limitations is from the 0 to 2 pi because the plane is rotated with the 360 degrees. So the range of phi is 0 to 2 pi. But z we know from minus infinite to infinite. Minus infinite to infinite. But the cylinder considered that is a cylinder height is the cylinder height is L. from the origin. So the distance of cylinder from origin to the point here, it's a length L only on the Z axis. So we are taking the Z is equal to 0 to L on 0 to L. That is a distance length of the cylinder. So after substituting here, integral dz is z, integral d phi is a phi, upper limit for the z is L, and upper limit for the phi is a 2 pi. Okay. So the remaining is a constant. So dr and small r is a constants. And for the phi, upper limit we have the 2 pi. And for the z, upper limit is L. We'll get the L only. So finally the Q is equal to 2 pi r. 2 pi r dr into L. So what is a dr now? Dr is equal to Q by 2 pi r. And we assume that it is a d bar is in the r direction, dr component. The dr we got the Q by 4, 2 pi L, 2 pi RL, 2 pi RL. The dr is equal to into AR bar, into AR bar. So now that we got the d bar is equal to Q by 2 pi RL into AZ bar. Okay. Now, here we have to know one thing. In this d bar is equal to, there is a 1 by 2 pi r. You can write it as 1 by 2 pi r in the side, and the Q by L and AR bar. This is actually we got the d bar is equal to. So what is this Q by L? Charge per length. So we know the change of charge with respect to the L is rho L. dq by dl is equal to rho L, and dq by ds is equal to rho S, and dq by the dv is equal to rho v. These are formulas we know. The change of charge with respect to the length is a charge density rho L. The change of charge with respect to the surface is nothing but charge density rho S. See here, there is no any change, means the Q by QL is equal to Q by L is equal to rho L. Q by L is equal to rho L. So finally, the d bar is equal to 1 by 2 pi r, and this function is a rho L. So I will do this a rho L into AR bar. Okay, there is a d bar, electric flux density d bar we got. And the relation between of electric flux density and electric field intensity is d bar is equal to epsilon naught into E bar. Epsilon naught into E bar. So we need the E bar. E bar is equal to d bar by epsilon naught. What is the d bar here? Rho L by 2 pi epsilon naught r into AR. R into AR. Okay, my dear students. So now we got electric field intensity due to the infinite line charge and electric flux density due to the infinite line charge by using the gas law. By using the gas law, we got the electric field intensity due to the infinite line charge. Got it, my dear students? And starting itself, I told that it is a E bar is equal to, here it is a rho L is a dq. That dq only after applying the integral values. Okay, d bar is equal to dq by, I told that is a 2 pi epsilon naught r into AR bar. Okay, the changing of dq and the d bar, nothing but it is applying after that E bar is equal to rho L by the 2 pi epsilon naught r into AR. Got it, my students? So we derive the expressions of electric field intensity due to infinite line charge by using the gas law. Next, you go for, see the electric field intensity volts per meter, electric field intensity, volts per meter. Now, the Maxwell's first equation. The Maxwell's first equation. Before going to the Maxwell's equations, okay, you see these also. Without knowing these Maxwell's equations, we can't derive the Laplace and the cosines. Okay, you can see this. We know according to the Gauss law, the psi is equal to Q and Q is equal to integral d bar dot ds bar only. D bar dot ds bar. Okay. So forget about what is a limit delta t and Q by del V. Simply saying that the point form of Gauss law of electric field, the point form of the Gauss law of electric field is that del dot d bar is equal to rho v. How it is means, let us see. We know the Q is equal to integral d bar dot ds bar. D bar dot ds bar. Okay, my dear students. And now I am checking here, this value is a surface integral. Is a surface integral d bar dot ds bar. By using the Stokes theorem or divergence theorem, the surface integral is changes to the volume integral. Volume integral is del dot d bar into dv. Okay, whatever the term we have, that is applied with the dot product with the del dot d bar into dv. So surface integral is changes to the volume integral. You can keep the dot product with the del of whatever the term is there in the dot product of the surface. So now we got the Q is equal to integral del dot d bar into dv. So forget about all these things, limitants and limitants something. Directly by using this Maxwell's first equation, according to the Gauss law, we know that Q is equal to, or the psi is equal to. So both are the same. Why the psi is equal to Q means a charge is enclosed in a closed surface. From the charge inside, there is a magnetic lines of forces is terminated and enters into, goes outside from the closed surface radially. And if we assume a small differential surface on the closed surface, whatever the flux that is passing through that surface is equal to the charge enclosed inside. The charge enclosed inside is a Q only. The flux lines out going outside is a psi. Then both are equal. The psi is equal to Q, and that is equal to d bar dot ds bar is a Gauss law. So I change the surface integral. I change the surface integral as a volume integral by applying the dot product of del dot d bar is equal to d. And now what is a Q? Q are, now only I told that it is a change of charge with respect to the volume. Change of charge with respect to the volume is the charge density rho v. Charge density rho v. And dq is equal to, what is the dq is equal to? And cross multiply, we'll get the rho v into dv. Rho v into dv. So now here I am applying the derivative on both sides. So dq is equal to d by something here. The derivative of integral, we know derivative of integral is a d bar dot into dv. Okay, derivative of integral will get only the constant del dot d bar. So what is a dq is equal to? What is a dq? Rho v into d. Rho v into d. Okay. Or otherwise, if you are confusing this one, simply you can write this change is integral value here and substitute the rho v by dv. Rho v into dV, or you take the integral here on both sides. Integral on both sides. Integral dV dq is equal to rho v into dV. Means q is equal to, what is a q is equal to? The integral derivative is a q only. Integral rho v into dV. What it matters for us? Okay. Here the change of charge with respect to the volume is equal to rho v, I told, and dq is equal to rho v into dV. Apply the integral on both sides. Integral of derivative will get the q. Q is equal to integral rho v dV. Now we can substitute here. Rectify ambiguity. Rho v into dV is equal to integral del dot d bar into dV. Now, on both sides, we have the volume integral. Remove that volume integral, and we have only the del dot d bar is equal to rho v. Del dot d bar is equal to rho v. This is a first Maxwell's equation. What they derived here is the same thing. Del dot d bar is equal to rho v. This is a volume charge density around a point. This equation called Maxwell's first equation applied to the electrostatics. This is also called as a point form of Gauss law or Gauss law in differential form. It's a point form we are calling it as. Okay, this is an integral form. Integral form is q is equal to integral d bar dot ds bar, that is equal to integral rho v, not the rho v, integral v, the volume integral del dot d bar into d. What it matters, students. So forget about this limit and whatever they are showing there here. Simply by taking the Gauss law, change the surface integral to the volume integral and substitute the q is equal to integral rho v d. Okay. The first Maxwell's equation saying that del dot d bar is equal to rho v. Okay. Next. Now, to derive the Cosines and the Laplace equations, you use the first Maxwell's equation, that is a del dot d bar is equal to rho v. Cosines and the Laplace equations. From the Gauss law in the point form, Cosines equation can be derived. Consider the Gauss law in the point form. Consider the Gauss law in the point form. Del dot d bar is equal to rho v, and here the d bar is a flux density we know, and rho v is a volume charge density. It is known that for a homogeneous or isotropic and a linear medium, flux density and electric field intensity is directly proportional. That we know the relation between of electric and the magnetic flux density, that is in the homogeneous one. Okay. You know, for that, for homogeneous and isotropic and the linear medium, flux density and electric field intensity is directly proportional. So d bar is proportional to the E bar. The proportionality constant is nothing but the epsilon naught. But it matters, friends. And now we know the del dot d bar is equal to rho v. Del dot d bar is equal to rho v. This is a Maxwell's equation. What is the relation between of electric and the magnetic the electric and the electric flux density, electric field and electric flux density? D bar is equal to epsilon into E bar. Now I am substituting here del dot d bar as epsilon into E bar. Epsilon into E bar is equal to rho v. Okay. From the gradient relation, this is a gradient V or del V is the relation between the grade V or the del V. So we can know that grade V or del V is equal to is a negative of electric field intensity minus del V, or E bar is equal to minus del V. Is a gradient V we can pronounce. This is one of the formula we have. E bar is equal to minus del V. Substitute here in the E bar as a minus del V. So del dot epsilon into E bar is a minus del V is equal to rho V. Okay, right. So first of all, I am taking the Maxwell's first equation, del dot d bar is equal to rho v, using the Gauss law of electric field. And the relation between of electric flux and the electric field is epsilon into E bar. Substitute the del dot epsilon into E bar is equal to rho v. And E bar you can represent it in the gradient, means minus del v. Now we got the del dot epsilon minus del v is equal to rho v. Taking the minus epsilon is outside as a constant. See here, minus epsilon as a constant. Inside we have is a minus epsilon. I bring it the outside. Inside there is a del dot, and here it is a del v is equal to rho v. Now bring the epsilon in the downwards. So del dot del v is equal to. So in the right hand side there is a rho v is there, and here in the left hand side the epsilon, cross multiply and keep the minus. So what is a del dot? Del means del square. Del square v is equal to minus rho v by the epsilon. Okay, my dear student, this we can call it as a Laplace equation. Del dot del is operation is called del squared operation and denoted as a del square. So del square v is equal to minus rho v dv, not the dv, sorry. Del square v is equal to minus rho v by epsilon. Okay. This equation is called the Cosines equation. This equation is called Cosines equation. If the certain region, the volume charge density is 0, in a certain region, the volume charge density is 0, which is true for dielectric medium, then the Cosines equation takes the form of is a charge free. There is no any charge on the volume, means there is no any density also. The charge free, so del square v is equal to 0 because the rho v is equal to 0. Rho v is equal to 0. What I am saying that the dq by dv is equal to the change of charge with respect to the volume is the rho v, and there is no any charge here. What is the rho v? Is the rho v is a 0. So rho v is a 0 means it is a free change, but charge free region it is. There is no any charge on the volume. Okay, how it is saying that is that there is a line is there, the charge is distributed uniformly, and there is a surface we have, there is a charge is distributed uniformly, and there is a volume is there, just like this, there is a volume. Okay, fully it is uniformly charged with all the surfaces considered as a volume. Okay, so there is no any charge here, and there is no change of that. So what is a rho v? Rho v is equal to 0 itself. So del square v is equal to 0 if in a certain region the volume charge density is 0, which is true for dielectric medium, then the Cosines takes the form of for a free charge of the free region. For a charge free region, del square v is equal to 0. This is a special case of Poisson's equation and is also called as Laplace equation. Laplace equation. The Laplace equation is a Laplacian of v, or del square v is equal to 0. Note that the rho v is 0, still in that region, point charges, line charges, and surface charges may exist at singular locations. It is not fully, it is a 0. You can say rho v is equal to 0. Okay. And the seventh equation saying that is a homogeneous medium for which the epsilon is a constant, but if epsilon is not constant and the medium is non-homogeneous or inhomogeneous, the equation phi, see here, the equation phi must be used as a Cosines equation for non-homogeneous medium. This is equation 5, we can say. Del dot epsilon of minus del V is equal to rho V. Okay. So with this, some part of the first unit we have remaining is there. Now you can see the another topic is the current and current density. Current and the current density. The current is defined as a rate of flow of charge. You know, the current means the rate of flow of charge carriers and is measured in the amperes. The current of 1 ampere is said to be flowing across the surface when a charge of 1 coulomb is passing across the surface in 1 second. Okay, the current I is equal. The current is considered to be the motion of positive charges. The current is considered to be the motion of the positive charges. The conventional current is due to the flow of electrons. Remember, my dear students, here the current is considered to be the motion of positive charges. The conventional current is due to the flow of electrons, which are negatively charged. Hence, the direction of conventional current is assumed to be opposite to the direction of the flow of electrons. Got it, my dear students? Here, the direction is very important. When the direction of conventional current is assumed to be the positive to the direction of flow of electrons. So, the flow of electrons is towards the negative real axis. The current is flowing into the positive real axis. The direction of conventional current is a conventional current assumed to be opposite the flow of electrons. The current which exists in the conductors due to the drifting of the electrons under the influence of applied voltage is called drift current. Okay. See, suppose if I am taking the voltage here and the current exists in the conductors, the flow of electrons in this direction, we can say it's any conductor here. Apply, that is, it is not the way to represent here. Suppose if I am using a one conductor, it's a conductor, let us assume. Apply here. Now the electrons is in this direction, the flow. The current is in this direction. The conventional current I is equal. So when the current which exists in the conductor due to the drifting of electrons under the influence of applied voltage is called the drift current. Okay. While in the dielectrics, there can be a flow of charges under the influence of electric field intensity. Such a current is called displacement current or convection current. While in the dielectrics, there can be a flow of charges. There can be a flow of charges under the influence of electric field intensity. And applying the voltage, there is any flow of charges is there, and the current is passing through that conductor. And that current is called as a displacement current or convection current. The current flowing across the capacitor through a dielectric separated into its plates is an example of the conventional current. The analysis of such current in the field of theory is based on defining a current density at a point in the field. The current density is a vector quantity associated with the current, and it is denoted as J bar. J bar is nothing but current density. Okay. The current density in the vector quantity associated with the current, and it is denoted by the J bar. The current is always the I, but current density is represented as denoted as a J bar. see here the relation between of current I and the J bar. Considered a surface S. See here. There is a surface we have. There is a surface we have. And I is the current passing through this surface. The arrow mark showing in the upwards, that is in the AN bar direction, and the current is passing through that surface. The direction of current is a normal to the surface S, and the direction of J bar is also normal to the surface S. So both the cases we can see, and J bar and DS bar are the normal, and the J bar and DS bar are not in the right angles. On that surface, we assume a small differential surface here, a small differential surface. Through that small differential surface, the current is passes. Consider the incremental surface area ds, the incremental surface area, a small differential surface area ds, as shown in the figure 5.1a, and an bar is a unit vector normal to the differential surface or incremental surface of the ds. Okay. Now, you see here the differential surface ds is equal to ds only. Okay, first of all, you can see that ds is equal to gs. So when this magnitude is a vector quantity, ds is a scalar quantity, ds is equal to ds. So now when it is a vector quantity, means ds is a magnitude and it having that direction also. The magnitude is a ds and the direction is a an bar. So ds bar is equal to ds into an bar, while current density. So in that current density, we can call it as J bar is equal to, through that differential surface, J bar is equal to, J is a magnitude and the an bar is a direction of the vector J bar. Current density J bar is equal to J into an bar. Okay. Then the differential current Di passing through the differential surface ds is given by the dot product of the current density vector J bar and the ds bar. The differential current passing through the differential surface, okay, a small differential surface, is the dot product. The relation is the dot product of the current density vector J bar and the ds bar is di bar. So di bar is equal to J bar dot ds bar. Okay, the relation between current density and the current. So when J bar and ds bar are the right angle triangles, so theta is equal to 90 degrees. Definitely, we know J and the ds, the small differential area, and it passes to that. And these are on the right angle triangles, J and the surface. Then the theta here, the theta is equal to 90 degrees. We know the di is equal to J bar dot ds bar. J is nothing but J into an bar. The magnitude is J and an bar is the direction. And the ds bar is equal to ds into an bar. Now, an bar dot an bar is equal to 1 only. So di is equal to J into ds. So I is equal to, apply the integral on both sides. Integral di is equal to I and integral J into ds. Integral surface integral J ds. Got it, students? Where the J is the current density in ampere per meter square. Why it is a meter square means it is passes through the surface. But J bar is not normal to the differential surface area ds. Then the total current is obtained by integrating the incremental current, which is the dot product of J bar dot ds bar over the surface. So for this reason, we are taking the I is equal to integral J ds is the dot product. But J bar is not normal to the differential area ds bar. The total current is obtained by integrating the incremental current, which is a dot product of J bar and the ds bar. So J bar dot ds bar is a current I is equal to. current I is equal to this. G is in ampere per meter square and the ds bar is in the meter square. Then the current of time is in the amperes. So what is the units of current is the amperes. G is ampere per meter square. That is the current density. Current density, the surface, the G bar is equal to ampere meter square, and the differential surface